Pleasure.
So thank you for joining. Let's wait again 1 minute more, just because we can see that there are a lot of people who are right now connecting to the session, and so we'll start in 1 minute. Okay, let's start the session. So thank you for joining this session. So as you can see on the title, this is a session on electromagnetism. So this is the episode 2 of a simulation series. So we already did one episode on e-bike. It was on modelization and simulation, the combination of both, and many different technical domains. So you can watch this first episode on YouTube. I will, at the end of the presentation, I will share the link of the YouTube channel where you can watch the replay of this session, and you will also be able to watch the replay of the today's session. So the main presenter of this presentation is Hassan. Hi, hello, Hassan.
Hi, Eric. Hi, all. Nice to meet you.
So just before leaving the floor to Hassan, please can you go to next slide? So please, if you have any question during this presentation, you can use the chat. So I think this is the Q&A section. So do not hesitate to ask any question about during this session. At the end, we'll take time to read your question. And if we don't have time to answer to all of these questions, don't I mean we will send you a reply, an email with the answers. Okay. Also very important, as I said, after this session, you will receive a link with the replay of the webinar, and also you will be able to watch the replay of this session and plenty of other webinars on the YouTube channel. Okay. So Hassan, I leave you the floor.
All right. Thank you, Eric. So, hello, everyone. My name is Hassan, and I'm actually the worldwide technical manager for electromagnetism at Dassault Systèmes. And today I'm going to show you what can we do in electromagnetism and why simulation it's important. Okay. So just before I start, I'm going to stop my camera regarding the bandwidths. Now everyone put a face on my name. Okay. So, if I want to start with something, this is a news that we heard yesterday, eventually, and we have seen on the news that France has forbidden from selling the iPhone 12 eventually. And the reason, because it didn't respect the European standards in terms of emission levels. And this is something you will see during the presentation. It's something very important. And if any phone or any, not regarding telephone, mobile phones, but any kind of electronic products, if those products, they do not respect the international standards, they cannot go into the market. Okay. And eventually, and unfortunately, iPhone 12 was not respecting at least the European standard, and this is why it has been forbidden from being sold in France. Okay, of course, I'm gonna give you a lot of examples from real life, and eventually another problem that happens with Apple as well. But we will see how simulation can help us to respect those standards and to predict eventually if we have any problem or not. So as you probably may have known, Dassault Systèmes sells what we call the 3D experience platform. And I'm going to show you today what is the electromagnetics engineer and all the application that we can see. And as I told you, I'm going to show you what can we do. And of course, I'm going to couple this with some examples from real life or from customers. So we're going to start just with this small question. If you can just have the time for like 1 minute or 30 seconds to answer this question. Okay, thank you, guys. I think we can go on. Thank you. Thanks, everyone, for your answers. And there we go. So we have a good number that knows what is electromagnetism, and that's nice. And for those who know it not very well or who do not know it at all, probably this is the time that you dive into the world of electromagnetism. All right? So what is the tool that is used behind the simulation? Is actually called CST Studio Suite, and CST stands for Computer Simulation Technology. And it's a company, basically, it was a German company that has been founded in 1992 by a German professor. And we got acquired by Dassault Systèmes. So we are a part of the Dassault Systèmes family since 2016. So usually we cover five domains, microwaves, RF, and optical, regarding everything that concerns intentional radiators, or what we call antennas, or any kind of hyper frequency or high frequency devices, such as filters, circulator, or anything like that. Then we do have the EDA electronics. So here we can study all the electronic boards that you can find inside your equipments. Whenever you open up an equipment nowadays, you can find those green boards. And this is actually the electronics inside. And of course, I'm going to show you what we can do with this. But of course, the EDA study, EDA, by the way, stands for Electronic Design Automation. It doesn't come alone, but it is tightly coupled to the EMC and EMI study, which is the electromagnetic compatibility or the electromagnetic interferences. You will see how those two domains, they are tightly coupled together, but sometimes we can have, electromagnetic compatibility studies that have nothing to do with electronics. And by the way, this Apple iPhone 12 that I spoke to you about, it was a problem of electromagnetic compatibility, okay? We also have the statics and low frequency applications, where we can study anything that goes from DC or static scenarios, such as sensors, or whether they are capacitive or inductive. But we can also go up to something a little bit higher in frequency. So we are here in the range of like kilohertz, and we have the possibility of studying the behavior of electrical motors, okay, for cars, for bikes, or any kind, even for home appliances, for example, washing machine or something like that. Finally, we have the most exotic domain, which is the particle dynamics, in which we are going to study, or we can study, the interactions between the electromagnetic field that could be created by any kind of device, and the charged particles. And of course, those particles, they could be electrons, they could be protons, they could be ions, and even they could be like simple dust, just for the story, we did have a test case in the Emirates, where the Museum of the Future, if you know it, they wanted to create a device that cleans dust with electrostatics. Okay, so this is an application with particle dynamics. Now, of course, with these five applications, we can cover the whole 11 industries that we have in Dassault Systèmes, starting from aerospace and defense, marine offshore, life science, transportation and mobility, even to life and home style. So please, now it is time to answer this second poll, and let's give you another like 30 or 40 seconds to answer. Okay, thank you very much. Great. So this is the agenda for today. As I told you, I'm going to speak to you about what we can do, or some examples for each of those domains that you have just seen before. And eventually, I'm going to give you some examples in real life. Okay, so let's start with microwaves, RF, and antennas. So if I ask you, or if we ask ourselves where we can find antennas, nowadays, I would love to say that we can find them everywhere, especially with the emergence of, Internet of Things. Now, everything that is around us is connected, whether it's a car, it's your watch, even glasses, mobile phones, everything is connected, right? And the key element to this connectivity is an antenna. Without antennas, nothing could be connected. So now antennas, they cannot be designed alone. They are integrated in their environment. So you can see here in the example up top with the high-tech industry, for example, you have a mobile phone where you can see that you have at least 8 or 9 antennas that could serve several protocols like 4G, Wi-Fi, GPS, 5G, Bluetooth, and probably in the future we will see more antennas like to cover the 6G applications, right? But of course, we also have in other industries like aerospace and defense, on an aircraft, whether it's military or civil aircraft, we can have up to 30 antennas placed on the same aircraft. And of course, each antenna is dedicated to a type of connectivity. But again, you can find them on industrial equipments like this bee excavator you can see here, or for example, this application here. What you can see here, actually, it's a remote control to turn off or turn on the light. It's a wireless switch. And on the transportation and mobilities, whenever you look at a car on the roof, you can see this kind of antenna, which we call the shark fin antenna. And it was actually, I guess it was designed by Audi. and they actually use CST to design it. And it's very important to include the radome that is up top, and of course you have the radars that can be found on frigates or civil ships. Now, the most important thing, and I come back to the fact that those antennas, they can never be studied alone. No one could say, okay, I designed a patch antenna and then that's that. Those antennas, they have to be studied in their environment. So you can see here, like if I take, this is the most talkative example. We have here the mobile phone in which you have the 5G array, and you can see the fact of adding a cover, on the top of the mobile phone. It actually has some influence on the radiation patterns, especially here. Before the radome, probably the most of the radiation is happening up top. But after adding the mobile phone, you can see here we have a kind of a waveguide that actually guides the field to the extremity, and it could be radiated here as well. So integrating the antenna inside the environment is super important. And if I go back here, this is another example of iPhone or Apple. I don't know if you remember probably this issue that Apple was facing, back, I don't know in which year, but it was related to the Apple iPhone 4. So the problem here is that a lot of users reported that if they hold their mobile phone in a given position, they would lose the signal. And this was completely a problem of what I just told you before. So the fact that this antenna wasn't studied inside its full environment was really a problem. So probably those guys, they have designed the antennas inside the mobile phone, but they have forgotten that this phone should be held by a hand. And the fact of putting the hand around the phone caused problems. And this eventually caused Apple costed them $175 million, which is not a very small number. Now, fortunately, the late Steve Jobs, he has a bunch of brilliant engineers, and they actually solved the problem by adding this small material here, and this is like a very noble material, I guess. It's not like plastic or, epoxy resin or something that emulates somehow the presence of a hand around the phone, and they were able eventually to shift back the operation of the antenna to where it was intended. So those $170 million, they could be avoided, and especially that this is only the replacement part, the cost of the replacement part. So without counting the engineers' time that, they solved this issue. Now, of course, adding more and more antennas to the same platform increases the capacity of a device. For example, here you have the Global Hawk military drone, and you can see that on it, you can find, in this example, you have 10 antennas. Each antenna is dedicated, again, to a protocol. But the fact that having an antenna, even though it increases the connectivity capacity of the drone, however, there is a dark side of it, which is the interferences. So, of course, studying the antenna in their environment is really important, but one should also study the RF interferences between all these antennas. And we have a tool inside CST that allows studying this interference, and it's called interference task. And basically, it gives you an output or an KPI like the picture you can see here. What you can see here is actually what we call the violation matrix. So you can see you have the transmission antenna, that the antennas that transmit signal. And here to the left, you have the receiving antennas. And whenever you have like a red square with an X inside it, it means you have interference and something should be done. Especially in military where the information, the transmitted information is really sensitive, you cannot allow yourself to be hacked somehow. And this is why interference study is super important to be predicted. Okay. Now, if we stay a little bit in the military domain, basically, if you probably search on the internet or ask any military guy that works in the Air Force, let's say, they can tell you that all the aircrafts that has been designed, they are designed in a way not to be detected by radars. And this is what we call actually stealthy aircrafts or stealthy fighter jets or even stealthy ships. Now, we do have the possibility in CST to study those kind of behavior, and this is what we call the RCS study or radar cross-section. So the idea here is to send a wave on the device or on the platform and see what is reflected back. Now, of course, we do have a lot of RCS type. First of all, we have the monostatic. Monostatic means we have only one radar. So this radar that could be on the ground or could be like here under the radome of this aircraft, what it does, it sends a signal, right? And then it has to detect the signal that is reflected back. And this is how the device or the target is, located. Now, of course, technology goes, I mean, it impresses us more and more. So those guys, they came with another tool because just how those military guys, they got rid of this monostatic RCS. If you go and Google and look, for example, for the B-2 bomber, that has been developed, I think, by Lockheed Martin. This bomber, actually, it's full of edges. Why it has been designed like this? Because when the signal is received, it will be diffracted everywhere except in the direction of the radar that has sent the signal. So in order to resolve this kind of monostatic RCS, now people tend to use what we call bistatic or even multistatic RCS. And by multistatic RCS, we mean that you have one radar that sends the signal, and then you have another radar that detects the reflected signal. So you see now the monostatic issue, it's the monostatic fact, it's not an issue anymore. So of course, in order to resolve this, those guys now they come with another feature that helps with reducing the RCS. They can use, actually, if I go back here, what we call radar absorbing material, or what we call RAM. So what happens there, for example, you can see here on the aircraft that probably the most part of the aircraft that contributes to increasing the RCS is the wings. So those guys, what they have done is they have added this material to the wings, and this material has the possibility of absorbing the signal and dissipate it. So nothing will be reflected anymore. So you can see here that with the radar absorbing material, especially in this direction, the RCS has been decreased drastically by tens of dBs. Now, of course, those studies, they could be extended to optical devices, of course. And as an example, I do have here a lens, it's just a spherical lens. And we do have numerical methods inside the tool that allow studying geometrical optics. So here what we have done is that we eliminated this length with a light wave, because light is considered somehow as a wave, right? We are in the part that light is considered as a wave and not as a particle. So we can have the possibility of sending a light wave here on the sphere and see how this light wave is focused with the lens, right? But of course, this could be done not only for lenses, but for radomes, for any other type of optical application, such as fiber optics or any kind of of devices. Good. Now it is time to switch to the second topic of today's, which is the EDA and the EMC. So as I told you in the beginning of this presentation, and again, if I go back to this iPhone 12 problems, 10 years ago or even 20 years ago, and even until now, a lot of those designers, as I told you, it doesn't even concern phones, right? It concerns any electronic product. If you buy any products nowadays, on the box, you can see like this product is FCC certified, or it's IEC certified, or like, it's QC passed, whatever. You have stickers on the boxes that says that this product has been certified. But in order to certify their product, the developers, what they used to do is that they go into this kind of lab. This is what we call a semi-anechoic chamber. They put their device here in a, they make sure that the device is operating. And here they have an antenna that detects the radiated emissions. Now, of course, as I told you in the beginning, we do have some devices with intentional radiators. So we do have mobile phones, for example, that have antennas. Those antennas, they are made to radiate energy. But believe it or not, for example, if you consider that, I don't know, inside your computer, the CPU is transmitting a signal to the memory. This signal, it's not intended to be radiated. However, since we do not live in an ideal world, and I mean the PCB inside the electronic board is super complicated, this signal could be somehow radiated still. And the idea of certifying this product is to make sure that those radiated emissions, this signal that has been radiated, doesn't go beyond certain limitations. And of course, those limitations, they have they have been defined in standards. And you have the American standards, you have the European standards, and of course, each standard, it has its own limitations. And again, if I go back to the iPhone 12 story, the limitations or the radiated emissions from the from the iPhone 12, sorry, they have respected the American standards, but they didn't respect the European standard, and this is why it has been banned from being sold in France. Okay. Now, the example of radiated emission, you can see them, they resembles to stuff like that. Of course, you have, because when the CPU transmits to the memory, for example, it sends like a square signal, right? And this square signal has a frequency, which we call the basic frequency or the band-based frequency. So you can see here we have a Dirac at this frequency, but of course you have all the harmonics at higher frequencies. And the idea is to see if those harmonics go beyond a certain limitation, okay? Now, of course, how to win over a bad luck. Why I'm saying this a bad luck? Because as I told you, up to now, at least 50% of those electronic producers or providers, they cannot have their products certified from the first time. So they go into this infernal cycle of development. So they prototype, they measure, they fail, they prototype again, they measure, probably they succeed, probably they fail again. So you see, this is an infernal loop. Getting out from this loop is super complicated. This is why simulation comes into this place, and this is why in the upcoming like 3 or 4 slides, I'm going to show you how simulation helps with that. Now, whether we're speaking about, when we speak about electronic boards, we do have what we call the signal integrity. We have the power integrity, we have the thermal integrity, and of course, we have the EMC. Once you have succeeded all those passes, it means you can put your device into the market. So, of course, this is the loop, or what we call the workflow. This is the complete workflow. And we start a workflow by importing the geometry. Now, inside CST, we do have the possibility of importing all kinds of PCB formats, whether they are, done in Cadence, Zuken, Altium, Mentor Graphics, IPC, whatever. But of course, studying like for the antennas, you cannot study the PCB alone. You have to consider everything. And this is why you can couple importing the electronic CAD data with the mechanical CAD data, because this motherboard and daughter boards, they are housed inside, housing. Do you have the USB ports that you have to consider? You have the antennas, of course, that you have to consider, the cameras, and all the housing of the phone. So how we do start the studies? As an example, we do have what we call here the signal integrity. So the signal integrity, it allows you to see you can see here how the field is transmitted, but this is also something very important to see here, that whenever you are communicating on a pair of lines here, you are coupling fields to the other pairs. And this is actually what causes the problem. Now, what is what is signal integrity studies? You take 2 components. I come back to the example of, I will give you another example that, that it's more talkative to those examples here. Let's consider that you have a CPU that is sending signal to the USB connector of the phone, okay? Or even of your laptop. Now, what happens is that the CPU sends square signal, as you can see here, the blue curve, right? This is a perfect square signal. But since the PCB, it's a really complex environment, this signal, the received signal by the connector, it will be the orange one. You see how much is distorted? So this is what we call the overshoot and the undershoot of the signal, which are caused by the complexity and, the thousand of, components, or probably the vias that you can find inside electronic boards. So those guys, they will definitely ruin your signal. Now, the thing is, we do not stop here. If you take the orange signal and you fold it on each other, let's start with this blue signal. If you take this blue signal and you fold it on each other, on itself, you will find yourself a rectangle by the end, right? If you fold a rectangular signal on itself, horizontally, you will get a rectangle, a perfect rectangle. However, if you take this distorted signal here, the orange one, and you fold it, you can have something like this. It's not a perfect rectangle, but sometimes we have like this shape. Or even if you go up in frequencies, this is a complete example and a comparison between USB 2, which work at 480 megabits per second, and USB 3, where the flow or the data rate goes up to 5 gigabits per second. So you can see here that the signal integrity is worse for USB 3. Why? Because for USB 3, we are going higher in frequency. And when we go up high in frequency, it means that this environment, electrically speaking, it's really, really complex. And you will distort your signal even at high frequency than in low frequency. But still, we have some specification. For example, the USB 3 tells us that if you have your eye diagram, this is what we call the eye diagram, by the way, guys, when you fold the signal on itself. When you have your eye diagram wider than this specification, it means you are good to go and your device is at least certified from a signal integrity point of view. Now, the eye diagram, you can have it like this, in a simple, I would say, curve, as you can see here on the red plots. But you can have it like this, with some color plotting. And this color plotting, it will give you some ideas on the bit error rate, for example. And of course, the bit error rate is the highest where you have here the crossings of all the signal. But inside, the transmission is amazing. So just to give you, for those probably who are not aware or who are not familiar with what signal integrity is, sending this blue signal, it's actually you are transmitting zeros and ones. We are speaking about digital signals. So if someone sends you a square signal like this and you end up receiving like a triangular signal, you will lose all the information, right? And this is why signal integrity is very important, because you have to make sure that your received signal or the device or the component that is receiving the signal will be able to decipher it, will be able where the zeros and where are the ones. Okay? Now, if we go to the other side of the certification, which is the radiated emissions, as I told you, the radiated emission, each standards, for example, whether it's the FCC or the the FCC standard, it's American, and the IEC, it's European. They both consist on designing the measurement setup like this. But again, instead of going into the lab and pay insane amount of money to get your device certified, as I told you, you can replicate what you have in the lab inside the simulation tool. So you can see here you have cables which are 1 meter long. Yeah, this is, by the way, it's set by the standards. Then you may have here what we call the LISN, line impedance stabilization network. You can have the DC source, and of course you can connect all of that to your device under test. And as I told you, you have those probes. For example, if we take here FCC 15B certification, it states that you have to measure the field at 3 meters, the radiated fields at 3 meters away from the device. So we see here we have the possibility of placing probes that will measure the radiated field. And as I told you, you can see all the harmonics of the transmitted signal, for example, or the radiated signal. And in our example of mobile phone, it is totally certified. Why? Because the radiated emissions are below the limitations where you can see here on the black lines. And just for your information, we do have a library inside our tool that can help you with setting up the limitation. So all you have to do is to say to CST, okay, I want to study my device with respect to military standards, for example, the military standard, the MIL STD 461. You can tell this to CST and it will help you importing all the components that are required to set up the simulation. But of course, it will define the limit lines to make your life easier by seeing if the radiated field goes beyond the limitation or not. But imagine your field goes beyond the limitation, how you can see where the problem is. Well, this is totally possible by seeing the electromagnetic field. So you see, we can see with the simulation tool, we can see the invisible. So you can totally ask CST to plot the electromagnetic field around the tool. And whenever you have hotspots, it means you have to do something on those hotspots, because those hotspots, the red areas here, those hotspots, they are the area with the most intense electromagnetic field, and they should be the one radiating. Now, of course, I have spoken to you about interference between antennas, but you have to be sure, you have to be aware that also interference exists between antennas and other transmitting lines. So once again, those transmitting lines, they are not intended to radiate, but still they radiate and they could interfere with antennas. So this is why we also have the possibility to get this violation matrix between antennas. And here you see you have a USB transmission line. And you can see if this USB is emitting a field to the other component or to the other radios. And by the way, just for your information, if you open a computer or if you open a mobile phone, you can see sometimes metallic shieldings around transmitting nets, or even a metallic shielding around a component. In that case, this metallic shielding is placed to decrease the interferences between these transmission lines, or even to decrease, this radiated emissions. Okay. Finally, again, if I give you an example in real life, when you hold your phone to your ear for like probably half an hour or probably an hour, you can feel the heat, right? And this is totally normal because your phone dissipates power. You have all the components here. You have the CPU that dissipates power. You have the camera. If you are using the camera, right, and you open the camera on your mobile phone and you leave it, after probably 10 minutes, you can feel that your mobile phone is really getting hot. And this is why the camera also dissipates power. And you have a lot, for example, the RFIC, it dissipates power. You have a lot of components, even the nets that are transmitting signal, they could dissipate power. And this is why we have the possibility inside CST to couple the electromagnetic study to a thermal study. And this is the example we did here on the phone. So you can see we have the possibility of doing a full Navier-Stokes simulation because we can consider the convection. You see the convection when you put, for example, if you turn on the stove in your kitchen and you put your hand away from it, you can still feel the heat because this is what we call the natural convection. So this is why we can consider this as well. So in our example here, we have the phone, the maximum heated area of the phone. It's beside the battery. So you see, it's really where the CPU and the RFIC are. And you see they could heat up to 49 degrees. Now, of course, 49 degrees, it's totally acceptable. This is why inside mobile phone, you cannot have fans, for example. If you take probably a net or a computer station, a book computer station, you can see that you have some fans inside those. And those fans, they are there because sometimes the CPU heats up really, really, really high and you need to have some air. And this is, we are in the forced convection scenario, and we can also study how the fan is cooling down your electronics. Now, of course, I've added here this arrow and I called it from 0 to infinity. Why? Because sometimes if the temperature increases really high, sometimes it can influence the material properties. An example, I don't know. Again, if you open up your phone, you have this green motherboard where you have both copper and FR4 materials. Bear in mind that those materials, they are really sensitive to the temperature. So if the temperature goes up, those material properties, they could change. And if those electrical properties of the material change, it could influence the full electromagnetic compatibility and the signal integrity studies that we have done before. Now, those studies probably that we have done before, they have been made at ambient temperature, let's say 20 degrees. But you can see here that the temperature goes up to 49. And it's very important to see how this temperature is affecting the material. And we have to restudy again the electromagnetic compatibility and the signal integrity. Because, we need our mobile phone to work at ambient temperature, but also if it even gets hot. Okay? So this is why we can totally couple the electromagnetic study to a thermal study, and then couple the thermal study to electromagnetic study again. And like this, you would complete the full loop and the full scenario, and you can be sure that your device will be certified. Now, of course, when we speak about electromagnetic compatibility, it's not only about electronic products where you have electronic boards, but a lot of people said that we may have someday electronic warfare, right? So we will have a war where no explosive will be used, but only, electromagnetics. And this is where electromagnetic compatibility is also important, because if I take here this drone example, now, of course, this is a complete civil application. It's the future of mobility. It's an air taxi. The electromagnetic compatibility study of this drone consists in ensuring that this drone will still be operational even if we have sent towards it a very high intensity radiated field. You know, if you send, for example, a very high radiated field to this device, it may take it down. It may shut down because it has a lot of electronics, or it have a lot of cables, as you can see here, because we do have the possibility of simulating cables, of course. Those cables could be connecting electronics to the controls, anyways. And the study here consists in seeing how much field is penetrating to the inside. Now, if you want military example, we do have another one, which is here. Here you can see, we call this the EMP. You know, the electromagnetic pulse bomb is something that exists even right now. But these kind of bombs, they do not affect humans. They affect only electronics. So what you can see here is the effect of electromagnetic, of an EMP bomb on an Apache aircraft. And this Apache, it has a lot of equipment inside where you have cables linking those equipments together. And of course, the idea is to study the transient behavior of, probably the voltage or the current that has been induced on these cables, but also to study the electromagnetic field that has been penetrating inside. So all those kind of devices, they are super important in the context of electronic warfare. So now I'm going to switch to the next application, which is the low frequency, and I'm going to jump right away into some examples. Now, of course, low frequency, I gave you the example of, the sensors, but we have much more than this. We have the, transformers for electrical grids, at 50 hertz or at 60 hertz, depending where you are in the world. But we have also those circuit breakers, which are devices to protect our, industrial equipments. You have also the electrical motor, so you can see how we can study even the rotation of the motor, the power, the efficiency of the motor. The example that you can see here, this is what we call the haptic sensor in a mobile phone. And one of its tasks is, this is the sensor that is capable of counting your steps. If you have your phone in your pocket and you are walking, this sensor actually is capable of counting your steps. But of course, we do have also applications such as inductive charging. This is typically the application of probably you have heard about the MagSafe of Apple. So this study, you can see that we are changing the position of the phone. And here you can see like a map showing you the efficiency of the charging. Now, of course, the efficiency of the charging, when your phone is placed in the middle, this is where you have the highest efficiency, right? It's between 80 and 100. Now, if I go to a real case application, what you can see here is a switchgear. Now, I'm going to explain to you what it does. You have here a three-phase switchgear, it's a three-phase scenarios. Here you have like kind of metallic material, which is copper, by the way, but in the inside here in the middle, you have a different material. So this material, actually what it does, it will melt if a high current, surges. If you have a high current surge, this material should melt. And again, here we come back to the certification of a product. We are not in the electronics anymore. We are in low frequency, but still those guys, they require certification. Now, what is the certification here? Of course, if you want to measure it, it's super expensive as usual. And the most common problem in those devices is the short circuit. Now, when you have a short circuit in those devices, it means you have a very high current that is flowing inside. I'm going to tell you in just a moment why we can have short circuits, by the way. So when we have short circuits, we have a high current that is flowing inside. High currents mean high power. High power means high temperature. And the idea behind this is to see if those guys here, the middle material will melt. Because if this material melts, it means the current will not flow anymore. And like this, you are protecting your equipment that is after. So you see, here the standards requires us to inject this short circuit high current. Of course, inside the standard, you have the value of this current. Probably it's something that is given here. I don't know if it's given here, but it's probably hundreds or probably thousands of amperes, that could flow inside this device. And the idea is to couple the electromagnetic study to the thermal study. And You see here you have the electromagnetic study because we have injected three-phased short circuit current inside those. We calculated the dissipated power, and of course by Joule's effect, we have studied the temperature rise on this material. Of course, you can see that it happens here in the middle. And of course, the idea is to inject this current for only 3 seconds, which you understood it. The thermal study that we had done here, it's actually a transient study. So you see, we have seen the increase of the temperature at 3 or after 3 seconds. So as I told you, the idea is to study the withstanding of those devices. And since I've told you that we have the possibility of studying the fluidic aspect of the device, the Navier-Stokes, you can see here how the velocity of the air that is around. But once again, this device inside it, you do not have air. You have SF6 gas. And I will let you know why we put SF6 inside those devices and not, normal air. But just to stay in the thermal behavior, you can see that the velocity or the speed of the air around, it's faster than the SF6. This is normally, or it's normal because the viscosity of the SF6 is higher than the viscosity of the air, and this is why the gas inside, it's less, the speed is lower than outside. And this is probably the opportunity to tell you that our tool can handle a multi-fluid domain. So it's not only one fluid, we can consider a multi-fluid domain. It could be 2 gases, it could be water and gas, it could be water and air, whatsoever. And of course, this is the temperature that is going on, or you can see how it increases through those 3 seconds. Now, of course, this is another example. It's not even confidential anymore because this is a paper that have been published between ourselves, the SOSystem, and G&W Electric, which is an electrical company in Germany. And the idea, again, was to study the thermal behavior of this transformer, and giving that this transformer is filled, or it's not even a transformer. Again, it's a circuit breaker like the one we have seen before, but same principle. But this transformer or this circuit breaker is filled with CO2. It's not SF6 anymore. But anyways, you can see here a very nice comparison between the measurements, which represented by the dots, and the simulation. And we even considered if this circuit breaker is filled with CO2 inside or SF6. Okay? Now, coming back to the causes of this short circuit, I told you that we have to inject short circuit current inside. Why? Because sometimes, before I give you or I explain to you what is this, we all know what is a taser, right? A taser, it's this device used to tase someone to protect yourself. How this taser operates, you just inject a very high current or a very high voltage inside the 2 tips, the 2 metallic tips that you have by the end of your taser. And the fact that this taser, it's inside air, and the air, it's well known that it's a weak insulator. It's really weak. So because the air, it's really weak insulator, and because of the fact that we are injecting a high current, there is this electrical arc that is created. So even though you do not have metallic stuff, the air, it's so weak to complete the loop and create this electrical arc. Now, of course, the taste is meant to create this electrical arc. But in our industrial equipment, we especially do not. We have to avoid this at all costs. And this is what actually causes the short circuits. Now, of course, since a lot of industrial equipment involve high currents or even high voltage, it's mandatory also to certify those products with respect to the creation or to the breakdown analysis. So again, the idea here is to inject the current that is intended to be used in the device and see if we have the electrical arc. So you can see here the prediction and the position of the electrical arcs and where it could be created. So this is why those guys, they do not have air inside, but they have like more strong gases like SF6 or CO2. But given that, nowadays, all the companies, they are going towards green energy and sustainability. So they are replacing the gases inside by normal air. Okay? Now, the normal air, it's known to be weak, as I just told you. So this is why there are some studies, and here again, you see we have a comparison. I mean, it's not a comparison. It's just just to say that the electrical arc here, the probability of the creation of the electrical arc is weak. But what those guys are doing here, we have just a test. This is a test example. It's not an equipment or anything, but this is like a test where you have a vacuum. It's not even air, because the air has some electrical conductivity. But in this device, we have sucked out the air, so you have vacuum inside. And the possibility is to study until what voltage or until what current we can or this device could withstand. And like this, the guys would know, if they want to create something sustainable with air inside or vacuum instead of those poisonous gases, what is the amount of the current that it could withstand. So now it is the time for the third poll question, if you would. Okay, thank you guys for your feedback. And it is time for me to jump to the last section of this webinar, because of course we can do much more than those applications. And this is like an example that I will show you in the oil and gas industry. Now, of course, whenever you are dealing with oil and gas, it means you have pipes inside the desert, where because those two applications I'm going to show you, they are for people from Saudi Arabia. So the first application is, you can see it here. Whenever you have oil pipes, whether they are buried in the sand or even they are underwater, like the picture here, you can see to the right. After some years, when you install those pipes, after some years, they could be subject to defect. For example, if you are underwater, you could be like, they could receive some kind of corrosion. And if you are in the desert, they could receive some kind of deflection. So you can see here how this pipe is literally got out of the sand. It's completely deflected. And this is not good for the flow of the pipe and of the oil that is inside. So back in the days, I mean, even I know until now, some companies, what they do is that they have a robot that can walk along all the length of the pipe, and it has some sensor on it, and it could detect eventually if there are some deflections or any other defect in the oil pipes. However, this is very expensive and it's time consuming, and it's really something, it has to be replaced if we have the solution. And of course, this is an example of a solution that you can see here. It consists in placing 2 coils or 3 coils. You have this big coil here, and you have that is emitting a signal. It emits a signal, or it's excited by a signal. And here, of course, this is like it's really shrink down just to fit here, but the distance between those coils could be up to some kilometers. Okay, so what is the idea? When the company installs the pipe, they calibrate it, which means they install the pipe when it's totally perfect. They excite this coil with a signal, and then they have 2 receiving coils here. They receive the signal on this coil, and they receive the signal on this coil, and they do a difference between the signal. They do the signal received here minus the one here, and they get this kind of signal. Okay, this is what we call the calibrated signal. But then, if probably after some years they want to inspect if there is any default, they just have to repeat the operation. And if the signal that is obtained is different than the calibrated one, it means that there is a problem. And of course, this doesn't only tell them if there is a problem, but it could also show them at what position they have the problem. So you see, it's a very quick, it's super efficient, and it's not time consuming at all. Now, again, we have another customer in Saudi Arabia that wanted to use our tool because, they use it to detect if a soil contains oil or not. So the idea here, again, we have a calibration, because imagine we are in an area in the desert, where we may have oil. What we can do is that we can characterize the sand, of course, because we do have the sand, we have access to it, we can characterize it. And then what the idea behind this is to send an electromagnetic waves towards the soil and to see what is reflected back. And again, if the signal that is reflected is different than the one that is calibrated for the sand, the people will know what is inside the soil, whether it's oil, whether it's water, or probably any other kind of material. So this is probably, this market, it's really niche for electromagnetics, but we still have the possibility to do some stuff, you know, in the oil and gas industry. And you see here, this is a comparison between the theory, because the first step of the user or of the customer was to compare the theory to the simulation. And you can see here we have 4 curves, but you see actually you can only see 2 because of the perfect correlation between the theory and the simulation that we have done. So there you go, guys. I think I finished my presentation. Thanks for your time, but I would like to ask you to answer this last poll question, please. Okay, thank you, guys. Thank you very much for your time. And if you have any questions, you can just send them, you know, in the chat or in the Q&A section. And yeah, I do have already 2 questions that I'm going to see from
Yeah,
Celso.
yeah, Hassan, during
Yeah,
you read the question and you work on your answer, I will just go to the next slide. Okay.
sure, of course, please
Okay.
go ahead.
Uh, Next slide, please.
Ah, there you go.
Yeah, so just for your information, we recently packaged a lot of learning experience. So learning experience are technical courses on our product and also on the physics. And we have released 5 let's say, learning experience. So this is really an accumulation of a lot of different courses. So for structural simulation, for fluid simulation, for Emacs, and also for multi-body system. And we also have one for all the simulation roles which are available on the 3D Experience platform. So as you can see, the price is, let's say, very low to compare to what it was to use before. Before, for example, it was around, let's say, between 100 and 200 just for one course, one class. And here in each learning experience, you can have, let's say, between 10 or 20, maybe 40 different classes. So this is really a new offer, very, very interesting. Okay. Next slide, please. Also very important, in a few days, so this is not the 6th of September, but this is the 26th of September, we will have a What's New webinar for SolidWorks. So you can take the picture of your QR code and you will be able to register directly for this webinar. So it's in 2 weeks. And in this webinar, I mean, we will present all the new feature of SolidWorks. Next slide, please. Then, again, very important, another QR code. This is the QR code to the official SolidWorks channel where you will be able to watch a lot of webinars, to have a lot of video content on, I don't know, for example, how to use 3D Experience, how to use SolidWorks, or different application for electromagnetism, for example, for EMC. So this is a very nice channel to have in SolidWorks. And next slide, please. Yeah, and over, let's say, channel where you can also follow us. So you can follow us for sure on LinkedIn, on YouTube, on Twitter, on X, let's say, because this is not Twitter anymore, and on Facebook. So I think you have a question in the chat, Hassan.
Yep. So I do have a question from Celso Almeida. I have a question. How do we import or create our PCB and 3D models into the simulation program? So we do have the possibility, as I told you, because you know PCB, they come in different formats, like from Cadence, from Zuken, etc. So we do have an importing gate, I would say, that allows you importing the PCB as it was designed in Cadence or whatsoever inside. And we also have the possibility to import any mechanical CAD model or geometrical CAD model that has been designed by SolidWorks or any other tools. But also, we do have a nice modeler inside the tool that allows you create shape on your own. So you see, you have all those 3 types. But even now in the version 2023, you know, we have the possibility of importing mesh, right? You can import mesh already. So you don't have to remesh the structure when you launch the simulation. You can definitely import mesh like from Nastran, or even if some guys they would like to couple you know, mechanical simulation to electromagnetic. so they can study how their devices are deformed. And this deformation or this deformed model could be imported as a mesh inside CST, and we can normally run the simulation.
So thank you, Hassan. I guess it
Pleasure,
does
guys.
answer to the question. Yeah. So we got really plenty of different
You're welcome.
format we can import.
Yes.
Thank you, Hassan, for this very deep dive presentation.
Pleasure,
We
guys.
saw a lot of different topics, a lot of different application, and this was only on electromagnetism domain. So imagine the other application we can have on the other simulation domain. So if you want to know more for on the other simulation domain, please stay tuned. Go on the SolidWorks channel on the we will have another webinar in a month also on multi-domain, multi-simulation domain application, which will be a mod sim application on industrial equipment. So please stay tuned, and I think we will keep in touch in a few days or in a few weeks.
Bye, guys. Thank you.